So in this second lecture in our discussion on time series, I'd like to introduce this idea of Bayesian state space models, which we briefly introduced in the last lecture. Bayesian state space models is not a specific individual model, it's more a framework for dealing with time series data when using dynamic process models. So the first part of a state space model is the idea that it is intended to allow us to fit and make predictions with dynamic models. So here, this process model is exactly kind of what we talked about in this last lecture of representing a dynamic model. Xt is some function of xt minus 1, potentially with additional lags, xt minus 2, xt minus 3. Here we're just going to start with the simple Markovian version, xt minus 1. Plus some process error. But in the Bayesian state space framework, what we're going to do is leverage the same ideas of latent variables that we did in the earlier discussions of linear models to account for observation error. And really, all the state space framework is applying the idea of errors and variables to time series models. We have this dynamic time series model with this latent state X. And what we then do is we write down essentially an observation error model, an error and variables model that says what we observe isn't X, but Y. And Y may be a direct measure of X measured with some observation error W, or Y may be a more complex proxy, or G may describe a calibration process. All the things that we talked about when we talked about errors and variable models, what those relationships could be between the observed variable and the latent variable apply here as well. So we have an observation error model between the X's and the Y's, and a dynamic process model for the X's. So if you think about that for a sec, that means that what we actually observe, Y, our data models telling us about this observation error, and then our process model is just only being run purely on latent variables. So this X of t is now never observed, it's a latent variable. This X of t minus 1 is not ever actually observed, it's a latent variable. And so we have this dynamic model. Our process model actually describes the evolution of latent variables through time. We'll see that gives us actually a lot of strength because the process model connects the X's through time to actually be able to estimate each of those latent variables. So if we look at this in our kind of graphical version that we've come to use to analyze models, our process model stage is describing this temporal evolution of our dynamic process model. We go from X at t minus 1 to X at t to X at t plus 1. To illustrate how a state space model works, I'm going to start with a very simple state space model, which is the state space model for the random walk. So in that case, there's not actually any process connecting X at t minus 1 to xt plus 1 other than process error. So at the hierarchical level, there's not parameter variability, and the only parameter that we need to understand is sigma, the process error. And that sigma applies to each of these X's. Actually, you can almost imagine it applies to the transition from one X to the next X. Then we have our data model, where we have these Y's, and Y's are observed through time. And then we have a connection between the X's and the Y's, which is the observation process, our observation model. And for the time being, for a start, I'll just assume that the only thing relating those things is a it's just an observation error. So, for example, just a observation variance. We'll call that tau squared. That applies to the relationship between each of these x's and y's. It's going to back up a sec. One of the things that's important to note about this state space framework, and one of the things that makes it so powerful, is that unlike a traditional time series model where you have y changing through time with some autocorrelation between those y's, that then we'll see in later sections leads us to having to generate these huge covariance matrices between all of our y's. Conditional on the x's, conditional on the idea that the dynamic process model underlying this is capturing the dynamics of the system, the y's are now treated as conditionally independent. So conditional on x, y of t minus 1 is not related to y of t, because we're making the assumption that the only thing that's different between the x and the y is observation error. So unless there is autocorrelation in the observation process itself, we can model the y's as conditionally independent. So if the observation error at one time point is different than the observation error at another time point, then these y's are independent of each other. It's only the x's that are dependent on each other, which is actually, we'll see, gives us a lot of power and allows us to relax a lot of the assumptions that are built into a lot of traditional time series models, which often don't deal well with things like gaps in data and missingness, that this framework handles quite naturally. So if we write out that model in terms of probability distributions, we have our process model, which we've seen before, our data model, which we've seen before, and then we have two parameters, a sigma and a tau, so we need to have priors on both of those. And here, just for simplicity, I've written down a normal process model. I've written down a normal process error, a normal observation error. And you don't have to make those assumptions. You can make, we'll talk about this later, you can make any assumptions you want in terms of the error model on the process error, the error model on the observation error. Likewise, I've, just for simplicity, assumed conjugate distributions for the priors on those, but you strictly don't have to do that. All of this will work just fine otherwise. The other thing that we need a prior for is the initial condition. So we need a prior on the very first x. And this is very analogous to when we were dealing with missing data models and errors in variables models, where we had a prior on those latent variables x's when they were missing or measured with uncertainty. Actually, the important difference between this and in those cases is that in a missing data model or these other latent variable models, we actually had a prior on every x. And here we don't have a prior on every x, we just have a prior on the first. And that's because if you think about what the process model does, is essentially it is providing a prior on xt based on xt minus 1, and a prior on xt minus 1 based on xt minus 2, and a prior on xt minus 3 based on prior xt minus 4. And that will follow us back until we need this initial prior on the initial condition. So in that sense, it's the random walk state space model. It is very much like a hierarchical model in that we are leveraging, we're kind of borrowing strength from each x on the other x's. Okay, so first we'd ask, what are the parameters that actually need to be estimated in this problem, in this model? The obvious ones are the sigmas and the taus. The non-obvious one is all of the x's. Remember that all of these x's are latent variables, so we have to actually estimate every single x as well as the sigmas and the taus. And that may initially sound if you think about it a little bit, that may initially sound impossible because I have, let's say I have n y's. I now have to estimate n x's plus sigma plus tau. So even this simple random walk variable, I have to estimate n plus 2 variables from n pieces of data. But the key here again is that these pieces of data are not independent. They're sharing information. So that's what makes that possible. So we want to figure out now what is our joint full probability distribution, and then what are the conditional distributions for each of those parameters. How would we actually sample each of these x's, sigmas, and taus? And I'm going to take a, particularly I'll end up focusing on the x's. So what are the parameters? The x's, the sigmas, and taus. What is the full posterior distribution, the full joint posterior? Okay, so the probability of our y's, sigma and tau given, our x's, sigma and tau given y's and any other information. In this case, there isn't any other information. Well, I guess the other informations are prior parameters. This is product of over all the observation models. So we have, the time evolution. Sorry, we have n data points, so we have n observations. We also have our dynamic evolution, our underlying process model. So we have our data model, we have our process model, and then we have the priors on each of these terms. Okay, if that was our full joint distribution, what is the conditional distributions? So remember, when we figure out conditional distributions, we just need to pull out the things that each of these parameters depend on from the full distribution. So if there's a term in the full distribution that does not have a sigma, then it doesn't end up in the conditional distribution. So if we want to estimate sigma, which is our process error, we have the prior on sigma, this inverse gamma, and then we have every term where sigma shows up, which is the x's through time. So we have n x's through time. We end up with n differences between xt and xt minus 1 that helps us understand the process error. And then similarly, if to estimate tau, we go and look over here about every place tau shows up. It shows up here in the data model relating y and x, and then it shows up in the prior. So we just need that prior, and then we need this product over all of the observations. In this particular case, you would see that there's conjugacy in each of these, so we can actually give sample both sigma and tau. But also note that if these were not conjugate, if you made different assumptions, we could still sample them conditionally. We would just have to use something like Metropolis from Metropolis Hastings if we chose non-conjugate distributions. Totally doable. Okay, and then if we look at the x's, this is the one that's usually fools people, because if we look at things, we'll see here we have this xt from xt minus 1, so we want to pull that one over. We'd see this yt given xt, so our process model gets pulled over, our data model gets pulled over. What folks often miss, though, is that if we have an xt relating to xt minus 1, that means we also have an xt plus 1 related to xt, and so xt shows up twice. It shows up once when we're predicting it given the previous time point, and it shows up again when we're using it to predict the next time point. So that means when we want to estimate any particular x, we actually have 3 pieces of information x to inform us about this particular x. We have the value of that x in the past, the value of that x in the future, and as well as the observed y. In this case, we've made the assumption that these are all normal, and that means they're going to all be conjugate, which means we can conditionally sample each of the x's conditional on the other x's and the y's using a simple give sampler. The other thing that's worth noting is if you think about one of the things we learned early on when we learned about the conjugacy between the normal and the normal, that was one of the cases where we had an analytical solution to that conjugacy, that we could write down this distribution in closed form. And what we found was that the precision when we combined normals was the sum of the precision. So if you see if we took this sigma squared, and wrote them both down as, say, S as 1 over sigma squared. If we wrote this as a precision, and we say we wrote down this tau squared as a T as a precision, 1 over tau squared, then the precision of our estimate of X is going to be the sum of these precisions. So the X is going to be more precise than any of them. And we'll remember that when we talk about some of the special cases here, when some of these terms end up missing. So we have our confidence in X is going to be related to the magnitude of our process error and our magnitude of observation error. We'll also learn that the posterior mean of this xt is going to be a weighted average of the other 3 components, each weighted by their uncertainty. So x of t, its mean is going to be a weighted average of x of t minus 1, x of t plus 1, and y of t, each weighted by their precision. So if this is, in this case where we have a random walk, we have no additional process. If we have very high observation error and very low process error, then the process, the x's are going to have the x of t plus 1 and x of t minus 1 are going to have the most effects on x of t. By contrast, if we have large amounts of process error but tight observation error, then the x of t's are going to largely reflect the y's of t's. And in between, we'll have something in between. So I want to next talk about 3 important special cases of the random walk state space model that kind of illustrate some of the strengths of the state space framework, and particularly some of how it handles missing data and how it handles how we can kind of seamlessly move from model calibration to model forecasting within the state space framework. So let's look at each of these. The first case, and actually quickly, let's go back and just remind ourselves, in the full case, we had 3 terms, and each of these 3 special cases are just going to correspond to when we're missing one of these terms. So in the first case, x0, we're going to say that this is x0 is occurring before y1, and so we have a prior, or x0 is informed by the prior on x0, and it's informed by the observation x1, but we don't have a y. We don't have a y0 in this case. We have a y is starting at 1. And so it's very often going to be the case where that initial condition uncertainties might be different than the process error uncertainty. Sometimes it's we have good field measurements on where the state of the system is at the beginning, and this initial condition uncertainty might be very well constrained and mostly reflect those observations and gain very little strength from the first data point. In other cases, we're starting a time series analysis, and the only thing we have is that first data point, y1, and so this might be a very broad uninformative prior, and so x0 is mostly informed by x1 and the process error. The last case corresponds to when there's not an xt plus 1. When there's not an xt plus 1, we only have the x in the past plus the current y. So we one of the advantages of the state space framework is the x's are constrained by both the future and the past. But when there's no data from the future, you're only constrained by the past. And then finally, this missing y case, if we're trying to infer an x and we don't have any y's at all, in the state space framework, we can actually do that. That x of t is just informed by the x of t minus 1 and the x of t plus 1. Yeah, and we were able to estimate this x of t. But if we go back and think about what we talked about in the last slide about the uncertainties, the precision of each of these estimates is going to be the sum of these precisions. And now in each of these cases, we're summing 2 precisions instead of 3 precisions. So these uncertainties are always going to be larger at the beginning of a random walk time series, at the end of the random walk, and then when there's any missing data. And that's not unique to the random walk. For any state space model, these reduced terms still apply. And then if we think about that last case, if I move from y of n, so from time n to time n plus 1, so I'm now actually moving into the future, that estimate in the future is informed just by the estimate of the past. There's not yet an observation. So when we're doing an actual forecast, there's not actually a y yet, and there's not an x in the future, so we get even less constrained. So when we move from model calibration to model forecasting, the state space framework handles that smoothly. It ends up eventually just propagating the process error through time into the future. And the uncertainties will increase as we do that. So how do we sample from this? So as we talked about when we went through each of these cases, all of them are amenable to Gibbs sampling. They were all normal or normal inverse gamma. The one trick here is that because you're doing things conditionally, each x's need to be updated sequentially, because each x is conditioned on the one before it and the one after it. So I might update, through the G, make an iteration through the MCMC, and the G plus 1th iteration of a Gibbs sampler of x is going to be drawn based on the G plus 1th updated version of x of t minus 1, but then the previous x g step of x of t. And so we'll kind of march kind of in a forward filtering way, march through the MCMC. Actually, one thing I wanted to go back to in this framework, and pointing out one of the strengths of this framework with respect to missing data, is that it allows us to very easily deal with missing data in the state space framework. And that can also mean irregularly spaced data in time, and or operating a process model that is operating at a different time step than the observations themselves. It basically gives us a very flexible way of dealing with missing data. Okay, so just to quickly sum up this general case, back to that general case, we end up with a model that is dynamic through time as our process model, and a observation model very similar to our errors and variables model that links the observed values to the latent states.